Hello. Okay, yes, hi. So I am from Harvard. I'm going to tell you about our recent experiments from this Harvard atom array team, where we're now kind of starting to build our processor and do our kind of quantum circuits, but with logical qubits. And it's no surprise to this audience that precise quantum computation has some key challenges. One of the key ones being that we need to use quantum error correction. And the typical estimates that are provided kind of on the more optimistic side is that we need scale of millions of qubits, coherence times on the scale of days for our logical qubits, and error rates on the scale of 10 to the minus 10. And this is quite daunting. And this is a challenge we're all very familiar with, and that's what we're all doing here. But a kind of other challenge, which is the main focus of what I'm going to be telling you about today, is that efficient classical control of these quantum systems has so far been kind of a major challenge. And in classical architectures, what people have gotten very good at doing is using something like 1,000 wires in order to be able to control something on the scale of billions of bits. Whereas in a lot of our quantum architectures, so far the way we've been developing our physical qubit processors is having multiple wires per qubit, which kind of goes in the wrong direction. And what I'll tell you about today is our approach to this problem, which are these reconfigurable atom arrays that you also heard about in a talk yesterday. And so what this looks like is we have this hyperfine qubit. And this hyperfine qubit has long coherence times on the scale of seconds. Then we use this so-called Rydberg state in order to quickly generate entanglement. And the coherence is so long in our system that we can actually move our atoms around. These atoms are trapped around, these atoms or qubits are trapped in optical tweezers that can be dynamically shuttled in the middle of the quantum circuit, even between, for example, multiple zones. And then we can move the qubits between subsequent gates, and then in this way kind of program complex quantum circuits. And the two really unique opportunities that will be borne out in today's talk is, again, the non-local connectivity in the system, but possibly even more importantly, it's the parallel and efficient classical control. So first, I'll just kind of give a lightning quick overview to how do we program quantum circuits with neutral atoms. This is a lot of stuff that we developed really only in the past 1 to 2 years. I'll kind of overview these various components, and then I'll tell you about our recent experiments using these for doing logical quantum processing. So just to start, this is how all of our experiments start, is with a MONT. This is not unique to our lab, and if anything, we actually have a small MONT. We only have roughly 10 million atoms in a roughly millimeter region of space. But something that's really apparent from looking at this is that there's a lot of atoms. They're cold, identical, and here we use rubidium-87 atoms. They're all cold, they're all identical, and they're essentially unlimited. So it's clearly not a problem to have atoms. The problem is in how to control all of them. They're already all right there, but now we have to figure out how to kind of efficiently take all of these particles and then assemble it into a quantum computer. And this kind of concept of doing efficient classical control is really baked into our experiment from the very beginning. You might have heard of a lot of kind of analog quantum simulation experiments from our lab and also throughout the field in the past few years, and it was kind of really relying on this efficient control of many qubit positions. And here what this looks like is we have our MONT inside of our vacuum chamber, and then we take a single laser beam and print it on what, here's one jargon word, is a spatial light modulator. And what this spatial light modulator does is it essentially acts almost like a computer monitor. It's an LCD screen. And then a light beam comes off of it and then gets split up into thousands of light beams just from this one device. Then we can trap scales of 1,000 atoms here. And then we use another set of optical tools, which is also really important. And this is called an acousto-optic deflector. What this lets us do in practice is with just two waveforms, one waveform for the X voltage and one waveform for the Y voltage, we can actually create dynamically programmable rectangular grids of light. And then we can use this to do parallel sorting of our atoms from this original configuration to something like a 400 atom defect grid, for example. And so that's how we control the positions of atoms. That's what we used in the past to, for example, make Kagome lattices, study spin liquids, and so on. But a kind of really important breakthrough in the field from several years ago is this so-called Levine-Pichler entangling gate, where, again, the qubit here is this hyperfine qubit that has long coherence times and very high fidelity single qubit rotations. And then we just use the Rydberg state for generating entanglement. I'll kind of skip through the details, but one of the really important aspects of our approach is that of so-called blockade. The interaction between two Rydberg atoms is actually so large that it's essentially infinite, and the gate just depends on the Rabi frequency. And in particular, the different computational basis states, only state 1 gets coupled to the Rydberg state. There's a collective enhancement of root 2 to the state 1, 1. And actually, just by having 2 clever laser pulses that are global, you can realize this CZ entangling gate. And what's so important about this in practice for what I'll show you today is now we're just going to use global pulses, and then we can just reconfigure the qubits in the middle of the computation, and that is enough for us to be able to program complex quantum circuits. So this is the first quantum circuit that we did. It's one of the simpler ones. It's making a 1D cluster state. This is from our work 1 to 2 years ago. And what this looks like is we put pairs of atoms in tweezers. Then we put everything in the plus state. We do our first layer of CZ entangling gates by just pulsing our 1 global Rydberg laser. Then we reconfigure half of our atoms and just shift them over just by changing this 1 voltage waveform. We pulse our second Rydberg entangling laser. And then just these 2 parallel steps, we make a 1D cluster state. And we probe here the cluster state stabilizer showing successful creation of the state. And really, again, the key takeaway is that through this blockade phenomenon, the position defines the gate. And we have, in our field, over the past few years, gotten really good at controlling the positions of many of these atoms. And now this allows us to efficiently control different types of complex quantum circuits. So this was our work from 1 to 2 years ago. The fidelity of this cluster state here was limited by our old 2-qubit gate fidelity. There's been a lot of progress in the field on this 2-qubit gate in the past year or so. So right now we're doing, now our gate fidelity is roughly 99.5% on here benchmarked up to roughly 60 qubits in parallel. And what I'll show you in today's talk, we're now operating on up to roughly 160 qubits in parallel. The gate fidelity is a bit lower, it's like 99.4%. So there's kind of like trade-offs there. Here we just made a variety of experimental improvements as well as kind of updating our laser pulse scheme. That's kind of one key improvement we've made. Another key improvement is being able to now do fully programmable single qubit rotations. So we can do an arbitrary single qubit rotation on any atom or qubit in the array. But importantly, we also really focus on parallelism here. So for example, so what we do is we use another AOD that we use our single qubit light through. And then if we want to, for example, address every other column or pairs of columns in the grid, we just display one waveform, and it kind of creates this rectangular grid, and then we can address all these atoms in parallel. And here you can see we can get this nice single site resolution. But still, we can do arbitrary rotations, but it also still it's parallel when you want it to be. And finally, in the field, people have kind of presented a lot of different solutions to mid-circuit readout with neutral atoms. All of them seem to work just fine. Our approach is that we take our qubits in the middle of the quantum circuit, and then we move them to a separate zone, which we call the readout zone, where we can separately measure these ones. We see that it doesn't affect the coherence of the qubits that stay in our entangling or storage zones, and we see that we can do high fidelity state discrimination. So this is our approach to doing mid-circuit readout and feed forward. OK, so that's kind of all of our technical ingredients in terms of programming quantum circuits. Now I'll start to tell you about our explorations of quantum error correction. So when we were kind of first discovering that this movement approach works quite well for programming quantum circuits, one of the things that we kind of bumped into almost kind of naturally is that error correction is a really native application of this approach. And one of the things we did was make a toric code on a torus by making periodic boundary conditions. And here what you're looking at is a movie where we're measuring the Z stabilizer by taking, there's 16 data qubits that are fixed in our SLM tweezers. We can put these tweezers anywhere. And then we have 8 ancilla atoms that are in rectangular grids that are rocketing around the system. And every time we put atoms into new pairs, we pulse our global entangling laser, and then this entangles atoms that are next to each other in a way that's also robust to the specific positioning. And what was kind of apparent from looking at this is that if we wanted to go to a larger toric code, for example, or if we wanted to make more toric codes, all this corresponds to is essentially a different SLM phase profile or a different waveform for our AODs. And it's something that kind of just directly scales and allows us to have parallel control over many qubits with only order of 1 classical controls. And kind of with this framework, what we're now going to be looking at is really focusing our control problem not on doing arbitrary single physical qubit control, but really focusing on how do we do single logical qubit control efficiently. And this is something that actually quite naturally multiplexes with optics. Imagine you have, for example, a grid of surface codes, and you want to do, for example, a transversal single qubit gate. This audience knows very well what you don't have to do is go and do something unique to each individual physical qubit in the block. You have to essentially just take one big beam and illuminate this one essentially big atom with this big beam. And we can do this and just in a single step do a transversal single qubit gate. But the thing that's actually really important is that what we can do as well is do this for 2 qubit gates. We can take our 2 logical grids, we can interlace them right on top of each other, just move the 2 grids right through each other, pulse our 1 global entangling laser, and in this single step, entangle the twins of the pairs of these logical qubits and do a transversal, high fidelity, fault tolerant transversal CNOT in a single step. So there's a lot of benefits of this approach, and it's going to be, this is really the key idea of everything I'll show you today. One aspect is that these transversal gates are inherently fault tolerant. So you don't necessarily even need to do, for example, D rounds of correction between each gate in order to maintain your fault tolerance. Also, from an algorithmic perspective, it gives you long range and direct connections between logical qubits. There's no swap gates. There's no kind of different ways of shuttling the information around other than just moving the qubits. And finally, this is a really important perspective from an experimental point, is that there's this efficient control aspect, which is that all physical qubits of the same block for these operations just receive the same instruction and act like a big atom. And this is what is allowing us to do now efficient parallel computation, but with logical qubits. And this is what our first generation logical processor looks like, again, with the really key focus of parallel control with only a few wires. And the transversal gate aspect I kind of already mentioned. It's a really important aspect of this approach. Then we have 3 zones. There's the storage zone, where we can store qubits for coherence times on the scale of seconds. Here they're not picking up any entangling gate errors, so actually we can store them there for quite a long time. You don't need to be constantly measuring stabilizers while they're in the storage zone. In our entangling zone, we can, for example, encode logical qubits. We can also pick up 2 logical qubits that we want to entangle from the storage zone, move them into the entangling zone, and then entangle them in a single step. Then we can, for example, move one of them back, or we can move it to the readout zone where we can, measure it mid-circuit and do, feed-forward operations. And of course, as you heard yesterday, the long-range connectivity is, special not only for transversal gates, but it's also special for exploring different types of codes. And it's kind of, a pretty broad platform for being able to study lots of different aspects of error correction. So as a first example of what we're going to do, we're going to just make 2 surface codes and do a transversal CNOT between them. So we just make 1 surface code in plus, 1 in 0, and then do a CNOT. And the way we do this is we make 2 surface codes. We just do a single round of stabilizer measurements. In this way, and then we do a single round of stabilizer measurements. We move the ancillas away into the storage zone. We do the transversal CNOT, and then we move the surface codes back. And we did this here for distance 3. A really important aspect of error correction, and something that was really, really nicely done by this recent Google experiment, is studying how these things scale with code size. And they showed that you can improve the idling operation as you increase the code size. Here we're going to be studying the transversal CNOT, and we went from distance 3 to distance 5. Previously, people have also entangled 2 distance 2 surface codes with ions. And we went to distance 7 as well with our 2 surface codes. And then here, what you're looking at is we're probing the logical Bell state that we make. This is for distance 7. We're measuring in the XX and ZZ bases, and you can clearly see that the 2 logical qubits are entangled. And in particular, what we see is that the error of the logical Bell pair that we create gets better as we increase the code distance from 3 to 5 to 7. And there's some pretty important caveats here in terms of comparing what are the different types of thresholds that can come up in a quantum circuit. So here we're just probing a single transversal CNOT, but what we'd really like to do in the future is kind of do many transversal CNOTs and see that by doing repeated correction we can not only improve the fidelity of one transversal CNOT, but we can extend the number of transversal CNOTs that we can apply, and that's one thing we're working on. Another kind of important aspect is that of how we decode. I'm sorry that I keep moving relative to the microphone. I'm too excited. So if we just do conventional decoding, where we just do independent minimum weight perfect matching within the 2 surface codes, actually the Bell pair gets significantly worse as a function of code distance. And so what we do is this technique we call correlated decoding. There's a theorist in our group, Maddie, who's leading this charge. It's a simple observation, which is that we're just doing transversal CNOTs. Errors propagate. So it's fault tolerant, but errors still propagate throughout the circuit. Errors can, for example, propagate from one physical qubit onto another physical qubit. In a sense, this is a bug. In a sense, it can also be a feature. So, for example, in Steen error correction, this is something you can use to actually, suppress errors. And the way we kind of model this mathematically is that when 2 logical qubits do a gate, we add appropriate edges and hyperedges to the system. It's extremely related to the space-time decoding concepts. And we also have some theoretical results, which is that this allows us to, for example, take the number of rounds per C0 that we need to do from D to something of order 1, and it also works for Cliffords and non-Cliffords. So, and kind of a key observation from this correlated decoding aspect is that once we're starting to perform these logical algorithms, especially with Cliffords, everything just kind of becomes a big stabilizer state. And it doesn't really make sense to consider individual logical qubits. You should really be considering the algorithm together as a whole, again, related to the space-time decoding. So that's one way we did this transversal C0. Another thing we did is we made 2 color codes. Here, just distant 3 color codes or Steen codes. And then we did a kind of ion-style experiment where we did flag-based fault-tolerant initialization. So we made a non-fault tolerant, 2 non-fault tolerant logical qubits. We used one of them as an ancilla logical qubit. We do this transversal C0 animation. And then this guy is our flag simply by post-selecting on our flag logical qubit. We can do this fault-tolerant state initialization. We see if we don't do the fault-tolerant state initialization, the logical error is roughly 2%. But if we do this fault-tolerant state initialization, we have this 99.9% spam, which, to the best of my knowledge, although I'm definitely open to being corrected, is worse only than the continuum group, but it's kind of also pretty close. And it's also significantly better than our physical atom, so it's kind of like a break even. And so what we see here is that the error correction can improve the fidelity of the state initialization, and also that we're kind of crucially relying on this transport-based C0 for doing effective logical operations. But importantly, we never really do things on single physical qubits at a time. Similarly, we never really do things on single logical qubits at a time whenever we can. So this here is, this data here is actually averaged over 10 total logical qubits, or 5 logical pairs measured in parallel. And once we can, fault-tolerantly prepare, for example, 5 different logical qubits, we can start to use them for algorithms. And here, what we decided to do, although there's many different options, is we made 10 non-fault-tolerant color codes. We decided to use 5 of them as ancilla logical qubits. And then we do this flag-based fault-tolerant initialization. We move these logical qubits to the storage zone. And then we make a GHG state with 4 out of the 5 logical qubits, again, which was just a random choice. And then we measure these with, the reason we chose the color code is the ability to do single qubit Clifford operations, logical Clifford operations. And then we measure the fidelity of our logical GHG state. With our fault-tolerant state initialization, it's roughly 72%. So clearly, genuine multipartite entanglement between the logical qubits. It's also better than if we don't do this fault-tolerant initialization. If we, post-select on the stabilizers of the computation logical qubits as well, which is an error detection approach, then the fidelity improves to 99.8, roughly, of the 4-qubit GHG state. And we also, with the Clifford rotations, we can also, for example, do logical tomography. So this is the tomography of our logical density matrix of this 4-qubit GHG state. And we can kind of really start to explore these early fault-tolerant quantum computations. And here is a movie of exactly how we make this. So we have our 2 zones here, the entangling and the storage zone. The readout zone is down here, and it's not used for this experiment. And we do 1, 2, 3 layers of parallel encoding steps. Then we do this transversal C0 on 5 logical qubits in parallel. We drop our ancillas in the storage zone where they're safe. We pick up 2 of our logical qubits and kind of start to slide them around and do these transversal C0s as they move around from each other, and then kind of drop them back off and then do our programmable Clifford rotations. So that's how we program these quantum circuits. And what you can see here is that this approach kind of really continues to scale. And one thing that's kind of a key feature of our approach is that there aren't really so many hard limits. There's a lot of kind of possible trade-offs and design choices. For example, here we actually used 280 physical qubits to make 40 color codes. We chose to use 20 of them as computation qubits and 20 of them as ancilla logical qubits, and did 20 transversal C0s. What this looks like here is we just repeat the same process that I showed you on the previous slide, drop them off in storage, pick up a whole new group from storage, do it again. There's some finite, roughly 1% logical error that we get every time we encode another 10 logical qubits in the way that we're doing this here, but we can improve that significantly. It's kind of starting to become really reminiscent of these, classical architectures, and it's inspired from classical architectures, where you have, for example, RAM that you can efficiently get information out of, process it in your classical CPU, and then put it back in RAM, at some cost of serialization time. That's one aspect of our zoned architecture. Another aspect is the ability to do, mid-circuit readout and feed forward. And here what we did is we fault-tolerantly made a 3 logical qubit GHG state. We moved the middle one to the readout zone in the middle of the circuit, and then measure it in the X basis, and then this projects the other 2 logical qubits that never interacted with each other into either the phi plus or the phi minus Bell state. And what we can do is we can always recover the phi plus Bell state if we do a classically conditioned logical S gate in the middle of the circuit. There's also, if we do not do the feed forward, of course, the XX and YY parity disappears because we don't have this phi plus or phi minus Bell state, because we have both the phi plus and phi minus Bell state. If we do the feed forward, then we recover the phi plus Bell state, and we see that actually if we instead of doing the feed forward step, if we just post-select on the middle logical qubit being in the correct state, then it gives roughly the same fidelity of a Bell state of roughly 78%. So it's just limited by the underlying 3 logical qubit GHG state, and the mid-circuit readout and feed-forward process is high fidelity. And the kind of time scale for all these operations here for the mid-circuit readout and feed-forward is 800 microseconds. It's significantly shorter than the coherence time of 2 seconds. I know people love clock speed, and this is something that we can, we have understanding in terms of how to improve by roughly a factor of 10. So, okay, those are various aspects of our logical processor. Another kind of aspect is that we're pretty impatient people. And so what we really want to start doing are kind of interesting, quantum algorithms with logical qubits now. And a really important feature is, not only doing, design of an error-correcting code, but also doing the design of the error-correcting code with respect to the algorithm that you want to implement, and kind of tailoring these two to each other, also with respect to what are your native hardware capabilities. And there's kind of this co-design aspect where we're considering all of these elements with respect to each other simultaneously. And in this, early fault-tolerant quantum computations, as we start to explore these things, these will really be kind of the spirits of things that allow us to kind of do interesting experiments much earlier on than we would have naively thought that we could do. And also, if we do it right, we might learn things that actually dramatically inform how we want to do things in the future. So here in particular, what we're going to study is generating complex states with 3D codes. Whew, man, I'm talking way too fast. Okay. Okay, so an insight here is that the way that magic is typically generated, for example, in these really nice resource estimations, and injected into a circuit is, fully general, and you can do, for example, HT decompositions, but it's also highly constrained. You're kind of making one magic unit, and you're teleporting it in, into a 2D code. There's also other approaches, but one of the questions we'll ask here is if by being less general, we can actually just natively generate a state that has a lot of entanglement and a lot of magic, and maybe if we're really clever, we could also use this as a resource state in the future. And so what we do here is we use this popular 832 code, which is the small 3-dimensional code. This blog post was extremely useful. This 832 code, it's distance 2 in the Z basis, distance 4 in the X basis, and encodes 3 logical qubits, which are given by the X face and Z strings, as shown here. And it has, a variety of really useful properties. It's a CSS code, so you can do transversal CNOTs, just like we do in our other work. But importantly, once these logical qubits are already entwined within the block, it actually turns out that it's pretty easy to entangle them because they're already kind of overlying on the same physical qubits. And actually, just by doing single physical qubit rotations, you can actually realize, for example, CZ gates and CNOT gates. You can also realize a CCZ, which is a really powerful non-Clifford operation, just by doing physical qubit T gates. And this sounds like cheating, because how are we generating entanglement just by using single qubit gates? But every time we go and do transversal CNOTs, we're going to pay back some of our entanglement credit and be able to do more entangling gates on the logical qubits within the block. And here we made 16 of these 832 blocks, which are kind of 48 small logical qubits. They're error detecting for some of the experiments we're doing here. Some of the experiments, we're going to use them also in an error correcting mode with our 128 physical qubits. And then we start to program complex quantum circuits here using these tools. And in particular, what we do is we encode everything in logical state plus. Then we do CCZ gates and CZ gates within the logical blocks. And then we do transversal CNOTs between the logical blocks. And then we kind of repeat this over and over again. This is our quantum circuit with our logical qubits. So there's 48 lines here corresponding to 48 logical qubits, 228 logical 2-qubit gates, and 48 logical CCZs. Kind of just for fun, but also because it's good at scrambling. We entangled everything on a hypercube. So we took these 3-dimensional cubes and then entangled them on a 4-dimensional cube. On the physical level, that makes a 7-dimensional cube. And it kind of scrambles things very quickly. And it actually turns out, due to our theoretical collaborators, that this actually relates to IQP circuits, which are a known kind of supremacy style type of quantum circuit. And so what we're going to do here is our sampling experiments, where sampling is you do a complex quantum circuit, you make projective measurements, and you compare the output distribution to the calculated one. And then we're going to quantify it with this infamous XCB, which is this weighted sum of expected probabilities with the observed probabilities, which is normalized from 0 to 1. It actually turns out, quite interestingly, our collaborators showed that for IQP circuits, XCB is actually a good fidelity proxy. What we see here, so this is for 12 logical qubits, where we can still kind of sample the entire distribution space. And we're looking at the logical bit strings. There's 4096 total possibilities. And what you want to do is reproduce this theoretical distribution. And what we see is that as we apply more and more error detection by progressively discarding more and more of our data, by just post-selecting on more and more stabilizers in the algorithm, we see that the fidelity continues to improve and improve and improve, and starts to really closely reproduce the theoretical distribution. If we quantify it with the XCB, it improves from roughly 0.2 here to roughly 0.7 as we kind of discard more and more of our data. And it's really useful actually for sampling. For example, for factoring, you would never want to throw out your data. You would want to kind of check if your factors work. But for sampling, it's really useful because you can't necessarily check whether your data worked. And now, for each bit string that we get, we also get a little confidence interval of how certain we are that this bit string was correct. And that's what we're doing here. And just to kind of show in greater detail how good the agreement is, so this is the theoretical distribution is in the orange, the experimental data is in the blue, and you can kind of see here across this entire Hilbert space, everywhere there's a theoretical peak, there's a kind of little experimental peak. If you kind of keep zooming in further and further, you can see that it kind of continues to agree. This is a 25 times zoom here. And all the way down to the 10 to the minus 4 level, you can see kind of these tiny little wiggles that get reproduced by the experimental distribution. And our current understanding is, so okay, the fidelity is not perfect, but something that's really unique to this logical implementation of sampling is that, although there can be errors, there's actually very few coherent errors, it turns out. And this is actually really useful for kind of reproducing this kind of distribution shape. And it's one of the unique features of using logical qubits. Okay, so that was for 12 logical qubits. We can also scale to larger system sizes. Here we went up to 48 logical qubits, and again, these many logical entangling gates. And what we see, we go to from 3 to 6 to 12 to 24 to 48 logical qubits, and we do the sliding scale error detection, where for 48 logical qubits, because of our error detection approach, we have to start throwing away a lot of data, so it's not like a scalable approach. But it's really useful for these kind of small scale sampling problems, or these sampling problems. What we see in all cases is a finite XCB indicating this successful sampling. We also see that the XCB score improves with increased error detection, showing the benefit of using logical qubits. Also, we tried to do this circuit with physical qubits, and it was so bad that it's not even on the plot. So it actually worked significantly better for logical qubits in our system. We upper bounded here how good our physical qubit implementation could be. It's roughly a factor of 10 or more worse than our measured XCB. Also, to the best of our understanding, although again, interested in being corrected otherwise, this kind of XCB score of 0.1 for kind of this level of complexity of quantum circuit is roughly a factor of 10 higher, or up to a factor of 10 higher than kind of comparable previous physical qubit implementations. It's actually a really complex circuit. 48 CCZs is well beyond the kind of 16 CCZs that Clifford plus T simulators can handle. It's also very non-locally connected, which makes it hard for example, tensor network algorithms. We actually had to structure the circuit in a very particular way such that we could, in a sense, kind of like really reduce the effective system size with a clever simulation technique, and still it takes roughly 2 seconds to calculate each bit string on our device. Okay, and then here's a movie of how we make this quantum circuit. So, okay, in the 1, 2, 3 steps that makes the 832 codes, and now we're going to kind of progressively do more and more layers of transversal CNOTs where we move these little rectangular grids around. I'm going to drink some water. We pick up the second group here and do the whole process again. This is kind of our serialization. We do the whole process again, and then we pick up the first group, entangle it with the second group, and that's how we make our 7-dimensional physical hypercube. So that's one aspect we studied is the sampling. There's lots of different interesting aspects that can be studied with these logical circuits, even in this kind of near term. So one of the other things that we did is 2 copy measurements, which are really powerful tools in quantum information. They can be used to, for example, extract entanglement entropy efficiently. They can also be used to extract information about all 4 of the n Pauli strings. And it's fully compatible with just doing some kind of scrambling circuit and a transversal CNOT at the end. And so here we made 2 copies of our 12 logical qubit circuit. We interfered them and then measured the logical entanglement entropy in the system. And what we see is that as we, again, progressively apply more and more error detection, we start to really nicely recover this characteristic page curve that you expect from this hypercube, which actually turns out to be a fast scrambler. And you see that the entanglement entropy grows, and then it kind of characteristically turns around and comes back near to 0 And this is kind of significantly better than we can do with our physical qubits. And the kind of theme here is that logical qubits, if you're clever, can already start to be used for interesting physics and quantum information explorations. So to summarize, how much time do I have left?
You got 3 minutes.
Cool.
More, actually. 7.
Oh, great. OK, perfect. So to summarize, we see that our quantum operations can improve with codistance. We kind of benchmark some fault-tolerant algorithms. I mean, all of our algorithms here are fault-tolerant because they're transversal. But here we also made the state preparation fault-tolerant. And then we did these scrambling circuits. So the kind of natural question is, what did we learn? And where do we go from here? So in terms of some lessons from our first generation logical processor, here are just a few kind of enumerated. So the main one, as has been emphasized before, is that the main thing that really enabled these experiments is the control over single logical qubits as the kind of fundamental units in the processor. And for example, this is the first time we made a logical GHZ state. This is the type of diagram that we draw for ourselves in the lab. We draw 10 logical qubits that we do 10, or we do here 5 transversal C-naughts between, and we think about the logical 2-qubit gates, we think about the logical single-qubit gates, we think about analyzing the logical qubits as logical qubits, and it definitely facilitates the process. We're not keeping track of all of the individual physical qubits in terms of our programming of the circuit as much. Another thing is that instead of considering individual logical qubits, you can get a lot of benefit from really considering the algorithms as a whole. This is, again, really related to the space-time decoding thing, and we use this correlated decoding technique. Another aspect is that logical qubits are not literally qubits. They're many-body systems, and sometimes they don't behave in exactly the way you expect. So one thing that can sometimes be a bummer is that the Bell state fidelity is not just given by the spam times the gate fidelity. It actually is a more complex process. But sometimes there's pleasant surprises with these many-body systems. For example, you get kind of things like inherently digital operation that we can see in our logical circuits, and coherent logical errors can be really suppressed. And already we're kind of starting to see that there are genuine examples where there can be interesting problems, where logical qubits can already outperform physical qubits. And a feature here is that the discrete gate set can be a curse if there's a specific problem you want to implement and it doesn't fall within this gate set. But conversely, if you have a specific problem that you can map to this discrete gate set, then it's one of the few things your logical qubits can do. So it's kind of actually something the logical qubits can do really well at. And for this early generation logical algorithms where fidelities are still limited and operations are still limited, there seems like there's quite a lot of unique opportunities that we can still be exploring, and there are going to be lots of interesting opportunities for doing early generation logical algorithms. So in thinking about the future, one thing that is really appearing throughout the neutral atom community that we're all kind of working toward together is that there's a really unique opportunity to build these kind of medium scale logical processors. We all kind of within the community understand that these existing techniques that we have can be scaled pretty readily to roughly 10,000 atoms, and the physical errors can be reduced from this 0.5% level to the roughly 0.1% level. There's important aspects that we're still working on, so we need to be able to continuously operate on our system and continuously reload atoms, which is one thing we're working on. And there's also a lot of unique opportunities. There's different choices of atomic species people are exploring, use of cavities, use of bias, use of erasure. Jeff and Trudy are here, and there's lots of different interesting aspects, and I think it's really a very collaborative approach. And there is a relatively clear path, it seems, to having something like 100 logical qubit device with 10 to the minus 5 logical error in the coming years. And this medium scale quantum error correction device may not necessarily, for example, solve huge problems, but I think it would be a really new tool for doing scientific discoveries, and it could really accelerate us along the path to doing large scale quantum computation. And so that's something that's pretty exciting for neutral atoms in the coming years as we kind of can continue to readily scale the techniques we have here. Of course, we're interested in getting to even larger scale processors. And to be completely honest, these numbers are still quite daunting. To have like a million physical qubits and this amount of logical error, even from an optimistic perspective, is quite daunting. And so there's possible avenues we're exploring here, like LDPC codes, like you heard about yesterday. Also different types of power efficient trapping mechanisms. Different ways to, for example, connect different modules, and there's definitely work that we're doing here. But the kind of main reason I want to emphasize that this is a really hard challenge is because we should really be looking for all possible breakthroughs, both from the hardware design, looking for different factors of 10 that we can squeeze out, as well as in the code design and the algorithm design, and really designing the codes and algorithms to each other. And it is at least in my personal belief that the experimentation that we do with the early generation logical devices in the coming years will likely dramatically reshape both the theory and hardware of how we think these large-scale logical qubit devices should be built. Thank you. That's the end of my talk, and here are my amazing colleagues.
Thank you, Dolev, for this really exciting talk. We have plenty of time for questions. So, one over there. Microphones.
Thanks for a great talk. You said you're impatient. You really need to for other groups to catch up. It's amazing. What I heard about neutral atoms is like the trap is kind of shallow, so you may just lose the atoms during moving around qubits. How do you address it, or is it not a problem anymore, or how?
So moving doesn't really cause loss for us. Something that does cause loss and is a big problem is the 2-qubit gate. So the 2-qubit gate, part of our error budget is the fact that there's atom loss. And we can suppress this. It's kind of at the 0.1% level every time we do a 2-qubit gate. We could suppress this probably by roughly a factor of 10. But if you need to do billions of gates, then we need to be able to continuously reload our atoms. And I think we all kind of understand this, and we're working on it. And I think kind of in the next year, I think throughout the community, people will present really convincing solutions.
I see. So you don't lose atoms when you move around qubits?
Not really.
Okay.
No, it's really the gate that causes atom loss.
Thank you so much.
There was a question over there. That was. Oh.
We've got a question here if you want to take it.
Yep.
Thank you.
Fantastic talk. Could you say a little bit more about measurement? You mentioned a measurement zone. Do you lose the qubits after measurement? Can you put them back into the computation? Can you do repeated measurement? How long does that take?
That's a great question. So here, our measurement is destructive, and it's a clear limitation. We only measure these qubits once. In our current attempts that we're kind of working toward doing repetitive error correction, if we have a lot of atoms, which we do, then we can kind of be kind of wasteful and do many rounds of measurement with just new fresh ancillas. But we are working on different ways of doing ancilla reuse. We have techniques such that in the near term we can reuse probably 90% of our ancillas. Down the line, you would probably want to reuse a little bit more by doing the imaging a little bit more safely. But also, we need to continuously reload the atoms.
No worries, thanks. Oh, just timescale, sorry.
Oh, timescale of the measurement is 500 microseconds. Hey, that could also be roughly 100 microseconds.
Okay, thank you for this talk. I'm interested in the sampling task using the logical qubits.
In the sorry?
So sampling task using logical qubits, and it seems that the XEB can be increased more for about 10 times.
Yeah, that's roughly right.
But at the same time, the acceptance rate is decreased. For example, 0.01.
Yeah, that's right.
In the terms of the quantum advantages or quantum supremacy, then I think it is better than it is better to use the raw data that is accepted rate is.
Oh, it's actually not so clear. I think it actually is really context dependent. It's a fantastic question, and I think so. And here we're not claiming anything about supremacy, but it's clearly something that can be explored. And so yeah, it's right. You throw away data, and your score improves, and you're essentially purifying your samples. And whether this is beneficial or not really depends on the regime you're in. There can, in certain cases, there can even be phase transitions as a function of your XEB score, whether it's actually hard or easy to simulate classically, in terms of whether it's hard or easy to spoof. So it's an interesting question. And it's true that we're throwing away, it's true. Mm-hmm. And it kind of depends on the regime you're in. Yeah. Mm-hmm. I think looking into the future, I mean, so one of the aspects in terms of sampling that people are interested in is kind of the asymptotic advantage, and physical qubits have noise, and so asymptotically there will always kind of eventually there will be kind of some finite scale. Logical qubits, what we're doing here, also doesn't scale because we're doing error detection. So one would also want to do error correction to have kind of truly scalable sampling if one was interested in that.
Yeah. So I think I'm just going to speak up. Thanks a lot for this very inspiring talk. I would like to maybe could you please comment a little bit more on the recent proposed erasure conversion protocol? I think we know that there are a theoretical paper last year, and this year we see people in the Jeff Thompson group. They have done very great work trying to achieve this protocol, but they have some limitation, like they cannot convert all the leakage into erasure, and you only have, I guess they can only convert like 1/3 portion of the eraser into the biased error, right? So from the lab side, what is the bottleneck or limitation from us to convert all the gate errors into biased error?
I would speculate that I'm not working on it, but I would speculate that the main bottleneck so far is that it's a really new idea, and so people still have to try it, and kind of perfect it.
Yep.
I think the estimates of how much you can convert actually could be much higher. And as Jeff would say, the more you can convert, the better. So there's kind of no cost to doing that. And I think it's one of the things that we should explore. I think we should be exploring all of these things, and kind of thinking about this medium-scale devices. Yeah, I mean, if we can get that erasure thing to work in the community, I think it could be really powerful. Yeah. And people are working on it. Mm-hmm.
Hi, thanks for the great talk. I have 2 questions. I think one of them might be a quick one. But I couldn't help but be intrigued when you were describing your 832 code thing, where you had like 12 blocks, or was it, sorry, you had 48 logical qubits.
Yeah.
And I think in a hurry, you said that you were demonstrating the use of the 832 code as an error detecting code, but you also said something about the error correcting mode. Did I hear that right? What is that?
Yeah, so for our 2 copy measure, so it turns out that for these kind of sampling circuits we did, that if you measure any of the qubits in the Z basis, it actually makes this problem easier. It's only hard in the number of qubits measured in the X basis, so it's really much more interesting to measure them all in the X basis. So it's all distance 2 there. For our 2 copy measurements, where the 2 copy measurement, you do a C naught, and then you measure 1 copy in the X and 1 copy in the Z. So there on the guide that was measured in the Z, we also did, we also applied a decoder.
Okay, and the other question that I had was more about the implementation of entanglement. But you talked about the Rydberg mitigated entangling gate that you have between 2 qubits, but I'm just curious to know if it is possible to do multi-qubit entanglement in this hardware?
Yes, it is, and actually in our Gates paper, which is online, you can find we also did CCZ gates with fidelity on the scale of roughly 98%, and yeah, it's absolutely kind of something like native multi-qubit gates is something that's really natural.
Okay, so and does the probability of loss get worse the more?
The fidelity is worse, and then loss is part of the error budget, and I mean it's going to definitely be worse than a CZ gate. But it's already a lot better than the kind of decomposition of CCZ into CZs and Hadamards and Ts. I mean there's trade-offs to doing it, but I think it's definitely I think these multi-qubit gates are definitely one of the things we're under-exploring in terms of clever ways that we can kind of get big factors.
Right. Thanks.
Yeah.
Right. Last question. Meanwhile, if the next speaker wants to start to make their way to the stage.
So I'm not very familiar with this architecture. I usually work in optics. So can you just give us a bottom line? Well, I don't know if it's bottom line or top line, but what is the biggest challenge to using this architecture for a fault-tolerant quantum computer? What's the biggest obstacle that you see that would need to be overcome for that to happen?
So I think to get to this kind of 10,000 atom scale and kind of 100 logical qubits with like 1 million gates kind of scale, I think it's actually quite promising. I think it makes a lot of sense. And there will be challenges to get there. I mean, one of the things we need to do is continuously reload our atoms. But I think all of these things are kind of, and you need to be able to constantly operate at this 99.9% fidelity. I mean, it's challenging, but I think solvable. Yeah, one of the things people love to talk about is clock speed. At this kind of medium, okay, fantastic. So at this kind of medium scale device, our estimates is that it would take, roughly, on the scale of, seconds or 10 seconds for us to, run a complex, kind of, million scale algorithm, and so it's still something, it wouldn't necessarily be a limitation there, but in parallel, we're also kind of exploring, ways to speed it up. Also, the kind of non-local connectivity does allow you to kind of win a lot in space-time volume. So, it kind of will need to be explored. And getting to the really large scale, I don't think we really understand how to operate with 10 million qubits. And I think that's something that we need to explore.
Thanks.
All right, thank you very much, Dolev. And with this, I introduce the next speaker, who is Guan Yu.